Hello and welcome back. If you follow the channel, you know that we have a little bit of unfinished business with our Russian space clock. This clock was part of the instrument panel of the Soyuz TM spacecraft and actually flew in space. In normal usage, the clock gets its timing signal from an external, high-precision time source elsewhere in the spaceship. Indeed, we were able to achieve atomic clock precision by driving it with a cesium source. But the clock also has its own internal quartz reference used as backup. If the external timing source fails, the clock automatically switches to this internal backup quartz oscillator. When we first powered up the clock, not knowing at the time it was running in a backup mode, we were slightly alarmed that it was a few seconds per day off. In hindsight, it is well within spec for the backup mode. However, we got a lot more alarmed when we found something more disturbing. The quartz oscillator appeared to have pronounced glitches, causing so much jitter that we could not even measure its base frequency. This got the comment section abuzz with suspicions that our clock was broken or that we did not power it up correctly. Regardless, this certainly looks abnormal. In this episode, we'll get to the bottom of it. We'll take a deep dive into the oscillator circuit, including reverse engineering the Soviet IC it's running from, and learn a thing or two about quartz crystal oscillators. See if we can find a culprit, and better, if we can or should do something about it. That's a clock signal at 1 MHz. You can sort of see how jittery it is. And then if you stop it and start to look at it, it's clean for most of it. And then you see these things where the oscillator seems to have a hiccup. And it goes fine for another while, and then here's another one of them. You can see how terrible that is. So we quickly suspected some switching power supply noise and added a probe to sense the power supply at the chip to see if there was any correlation with the glitches. And here I have the power coming to the chip. And you do see there's this very small glitch in power that is totally synchronous with the glitch we see in a crystal oscillator. It's super small, so the power is not causing it, but it's something that has to do with power. So I've made a little sniffer here because we suspect the problem comes from the power supply. Can you hold it there? And I can zoom on the... I can see it. There we go. So you can really see the chopping frequency and the two glitches in the clock. You would think a decoupling capacitor would get rid of it, but I tried and it didn't. I even tried to put a decoupling cap on the clock circuit, and that doesn't do it either. You can just see it. There's some coupling in the quartz circuit itself. So unfortunately, this is not going to be an easy one. Although it's clearly from the very sharp switching spike you see here in the green trace, it does not come to the board via the power supply lines, and adding the coupling to the supply on the chip itself did nothing. It must be entering a sensitive spot in the oscillator circuit itself through some kind of electromagnetic coupling, and it's going to be too hard and too dangerous to debug on the clock itself. So at this point, I decided to rebuild the same circuit outside of the clock so I could debug it. So here is the replicated oscillator circuit, the 1 MHz quartz oscillator. But before I go there to build the circuit, we first had to find the Russian chip. And fortunately, there were 3 on eBay, which is perfect because there is one that I use for the circuit. There is one here that you can admire for your enjoyment. And there was a third one, and that one went straight to Ken Shirriff, so he could decap it and reverse engineer it and find what it is. And there's no direct equivalent in the TTL series, but you will see that it is very, very heavily inspired from the 7403 quad open collector NAND gate in the TTL series. And Master Ken just decapped the Russian chip that has the oscillator going.
It's a very pretty chip with a very nice layout. It's a bizarre chip that doesn't have any American equivalents. It's 4 NAND gates that are open collector, and then it has 2 pull-up resistors that are wired externally, so you can hook them up however you want. And so looking at the chip, we can see that here. Here's your VCC, your 5-volt input on this pin. And then these 2 thin pink stripes are 2 resistors. And then you can see they're wired to these 2 external pins through the white metal layer here.
So those are bonus pull-up resistors.
Because they're open collector, you need to have a pull-up resistor. And with the Russian chips, they give you those pull-up resistors.
Yeah, well, we never thought of that one, right? 3 resistors, comrade.
And then the other interesting thing is VCC is connected through this high resistance wiggly resistor here to the base of this transistor. This is one of the strange things about TTL, is that you have multiple emitter transistors. Each input gets its own emitter. And so you can see these 2 connections up here are your 2 emitters. So that's the 2 inputs for your NAND gate. And then the collector here comes from your 2 emitter transistor and then goes over to this transistor, which is basically buffering it for the output. And then the larger transistor here is the output transistor. It's larger, so it has the higher current for the pull down.
So where are the 2 inputs?
That would be here. So these 2 spots here are the 2 emitters, and it's wired to here and then off the top of the screen. And then you can see that this input, one of the other strange features is that there's one input that's wired to 2 different NAND gates.
Oh yeah, yeah.
So you can see it's wired to this one and it's wired to this one.
And we had such a trouble reading the spec sheet with how would you do that? Huh?
And you can see there's 2 large output transistors that they didn't use. So they probably used the same die with just a different metal layer to produce different products.
For different circuits. So although the wiring of the chip is slightly unusual, and we get 2 free resistors for the people, the schematic of the NAND gate should be pretty familiar. Here's the TTL 7403, and here's the Soviet chip, don't blink, the Yankee version again, the Soviet one, yeah, you get the idea, it's exactly the same thing. And after we had reversed engineered the IC, the only thing we had to do is figure out the circuit, and Ken did a fantastic job at it. And this is what the oscillator is. It uses 3 gates and a little bit of a 4th one. But really the heart of it, and you'll recognize it if you have a keen eye, is these 2 gates that form a ring with the quartz crystal. So this is called a series resonant oscillator. And if you look at the smorgasbord of oscillators with quartz crystals, they are basically trying to do this fellow here. 2 inverters and a crystal that comes back. And you see inverter 1, inverter 2, and a crystal that comes back. And so there are a few subtleties to this. Here, instead of using an inverter, they use an AND gate, so they pin this one to a positive level. And instead of putting it with a resistor to the positive, they just use an inverted gate tied to negative. I guess they had a free gate, and that saved them a resistor. And they have 1 extra stage here to act as a buffer, basically as a logic amplifier to isolate the clock signal at the output. But in order to understand how this series oscillator work, we have to look into more detail at what a crystal does. So what's a quartz crystal? Well, it's actually just that. It's a piece of quartz which is a crystal. So like a crystal glass, it will have a nice resonance on it when you ping it. And on top of that, it has the property of being electrodestructive. So you can actually actuate it by putting electricity on with two electrodes at the top and the bottom. And if you do that, it will actually actuate, it will start to move the crystal. And vice versa, if the crystal moves, it will induce a current on the electrodes. So it's kind of a mechanical resonator with conveniently integrated in it an actuator and a sensor. And the goal is to make this resonate at its natural frequency, which actually only depends on the thickness, doesn't depend on the area, so it's very easy to control. And electrically it looks like this. So also it behaves electrically like a resistor, a coil, and a capacitor in series. Those are all mechanical elements. The coil represents the mass of the crystal, the capacitor represents its springiness, and the resistor are the mechanical losses. So in parallel to that, you have the capacitance of the electrodes, that's actually really electrical, and also the parasitic capacitance of the package. Of note is that the resistance pretty low, is in the 100 ohms range, and there is a big difference in capacitance between the mechanical capacitance and the electrode capacitance. So it's almost a factor of 1,000 between the two. This is in the picofarad range, and this is in the femtofarad range. So that will become important when we look at the mode of resonance, of which this has two. The first one is the actual mechanical resonance, is when this coil resonates with this capacitor, and this basically the pendulum resonance, and the circuit becomes essentially, this cancels out and it becomes this, and the other capacitor doesn't really matter here, so you get 100 ohm, and that's called the series resonance. So that's what our circuit is based on, and basically you would use it in a circuit that looks like that to make a filter, right? Away from resonance, this is fairly capacitive, there's not much that goes through, and at resonance it becomes resistive, and all of a sudden your signal goes right through, and we'll look at it in a second. It's very peaky. There is also another mode that's called the parallel resonance mode, and that's basically when the coil here resonates with this capacitors and this capacitor in series. So it's called a parallel resonance, but the caps are in series, and it's basically, think of it as like this: the capacitor, the other capacitor, and this, and also we probe it over here. Think of it as if we were probing it over here, and so this looks like a circuit like that, like that, like that, like that, with 10 femtofarad and let's see 10 picofarad. And when that is resonant, then that's the impedance, instead of being the lowest as it was in the series, it becomes the highest, and that you would use in a circuit like this, where you put the filter across, and basically when it's off resonance it shorts your signal, and it shorts it very much when it's at the series resonance, and at the parallel resonance it becomes very high impedance and your signals go through. And that's called the parallel resonance, or because it's used in a parallel circuit like this, or the entire resonance. So the parallel resonance will be a tad higher in frequency than the series resonance, because it sees the series of the two capacitors. So let's do a little bit of practice. This is a quartz crystal at 1 megahertz, and I've put it in this little fixture, so it's actually in series across the two connectors. And I'm going to connect it to my pride and joy, the HP VNA, vector network analyzer, and it's going to give me the response. And the curve you see here is the signal that goes through the crystal. It's basically measuring through versus frequency. So it starts a little bit below 1 megahertz and stops a little bit after. We have like a span of 5 kilohertz around 1 megahertz. And you can actually see the two resonances. If I put the marker, here we go. So here is the first one, and that's the mechanical or series resonance. And then, as predicted, a little higher in frequency is the one where it also resonates with the external capacitance, and that's the anti-resonance or parallel resonance, and then it goes back. Now, one thing that this instrument sees, it not only sees the amplitude of the signal, but it sees the phase. And let me show you the phase if I can go through the complicated menus. There we go. There we go. And so now the blue curve is the phase, and you see that something quite dramatic is happening. So I'm going to follow the blue marker over here. So away from resonance, it basically looks like the capacitance of the electrodes, so a few picofarads. So it's a capacitor, so it has plus 90 degrees phase change. Then at resonance, look what happens. It just precipitously goes down, and at the exact resonance, it hits 0, which means it's become a resistor. So it's at electrical resonance there. Then you go past resonance and it's minus 90 degrees almost. What does that mean? It means it has become an inductance. And now the phase shift is 90 degrees. And the same happens on the other side. At anti-resonance, it becomes resistive again. And it goes back to capacitance. Now the reason I'm showing you the phase is that it will become quite important when we review the oscillator circuit, and the phase in the crystal has to be very particular for it to resonate, for it to oscillate. What else? Oh yes. So why did I buy a 1 megahertz crystal and it's neither 1 megahertz at the resonance or at the series resonance, nor 1 megahertz at the parallel resonance? It's because this crystal is a parallel resonance crystal, and it's specified with is parallel resonance with a specific capacitance load, and you cannot see it, but here it's written 13, which means actually to get to the frequency written on the crystal, I have to measure it with 13 picofarads as a load between the leads. So let's try that. So I have now added my little capacitor load in accordance with the manufacturer's specification, and we're going to try it again. And now you see that it's giving me the right answer. Where's my marker? So now if I go at the anti-resonance, it's been pulled up by the higher capacitance. Now if I put infinite capacitance, it will be right over the mechanical resonance. And it reads now 1.0005 megahertz, whatever this. So we're right on the money. So interestingly enough, the circuit we have here is not a parallel resonance circuit; it's a serial resonance circuit. So it will not oscillate at 1 megahertz, but a little bit lower at 999.8 something. So now we can complete the explanation of our circuit, the long explanation. So what this is, these are two logic gates transformed into amplifiers, and how they transform into an amplifier is by putting a feedback resistor between the output and the input, so that will bring it just in the middle of the state. It will be in equilibrium about halfway at 2.5 volts and ready to amplify the signal. So here is one inverter. The capacitor here is just so that the bias of the two do not interact. So it's just a DC block, so a fairly large capacitor. Another amplifier here. The resistor here is the famous pull-up, the people's pull-up resistor. It's inside the IC. And then you start from here. You get an inverter that's 180-degree phase. You get another inverter. It's 360. So we're back on our feet, and this will oscillate if the phase here is 0, which turns out to be also at the place where it has its peak transmission, and it will therefore oscillate on the series resonance. Now this resistor here has two functions. It limits the power in the quartz, so that's better for aging. It also prevents the feedback from the B point to knock the crystal too hard and get it off a nice resonance curve. And that's about it. So let's go test this thing and see if it oscillates. Okay, so now it's come time to test our circuit. So here's our replica oscillator. It's the exact same that's in the clock, hopefully, or close enough. And right now I have it powered by this 5-volt power supply, and I'm looking at it on the yellow curve on the scope. And with a little bit of chance, it should oscillate. And it actually does. And it, as you can tell, there is no jitter, so the circuit looks perfectly fine. And it oscillates at 999.75 kilohertz. So as predicted, it's on the series resonance, it's a little bit lower than 1 megahertz. So far so good. Now let's see if it's affected by the clock power supply, which I think is generating problems. So I'm going to turn the clock on, and I am also measuring the oscillator of the clock on the green. So now it's on. And sure enough, look at that. You can see that all of a sudden I'm starting to have some jitter. I even saw some extra pulses. Let me see if I can. Where is my trigger? I can catch one. Yeah, I can see it one here. It's hard to trigger on those because they don't come often, but you can tell that it's completely affected by the clock. If I turn it off, it's good. And those are not even connected, right? They are just next to each other. So next step, I'm going to connect them to the same power supply, and then I expect it to get worse. But definitely we're on to something here. It's picking up some of that chop signal into the Quartz oscillator, and we're going to find in a minute exactly where and why. So now powered by the clock power supply. And well, it's just, you know, it reproduces pretty much exactly what we had with the original oscillator. It's not as bad, it's not that much worse, right? It's just... And then let's bring out another probe. I think I have it already hooked up. Yes, this is hooked up and measures power. So get me the glitch. And then if I trigger on the glitch, so this is now power, which is this dirty rail is catching up something. So once again, it's not from the power supply, it's the power lines also catch up this very high frequency noise. From the power supply, if I measured it, it would be nice and flat. So it's just from the whole circuitry is getting some kind of awful emission. Trigger source. Let's trigger on 3. There we go. Okay, oh, so what I need to do is this. Right, exactly. So you see exactly what's happening. That's That's a very high frequency noise actually. This is 1 megahertz. This is easily 10 megahertz. And the switching frequency is 40 kilohertz. So this is something that's generated at the switch, and it's very high frequency, and it pollutes about everything. So you can tell on my little outside clock, it's annoying it, and on the inside one is making big spike because of course it's closer, it's right in it. And as a further proof that this high glitch at 10 megahertz radiates everywhere, I'm going to remove the blue probe from over here and from the ground, if I can. There we go. And I'm now up in nothing. There you go. You can. So I'm just not connected to anything, and this is a very well grounded and shielded probe, and still, but it's whatever is over there. Probably a switching transistor would be my guess. Alright, so we know the source of the issue. Let's figure out how it gets into the circuit and if we can get rid of it. Okay, and here I have a little stash of components I'm going to use to try to tame the circuit. The first one I'm going to do is kind of obvious. I'm going to put a decoupling capacitors, 100 microfarad, just we get that out of the way. I don't expect it to do very much. Okay, so I've put my decoupling cap, and as expected, it's better. Actually, it's quite a bit better, but it still is having a lot of jitter here. And probe the circuit with my finger, which is a good antenna. If I touch the quartz, it gets terrible. If I touch the output of the quartz here, so I'm touching the 10K resistor here at the beginning of the chain to see what kind of signal I have. So while I'm doing that, I'm going to make it worse because the probe is going to pick up some noise. But okay, so that's the quartz. So I can see the look at that spike. It's like a spark gap radio, and it's getting into the quartz. So that's going to have some effect, but I wouldn't expect it to be nearly as bad. So let's move away from it. Try not to short anything. Let's move behind the gate. So now I am probing at B. So that's after the amplification through the gate, the signal is much smaller than I had at D. So it has been tremendously attenuated over here, and it's of course now super sensitive to noise. So that's where I'm picking it up. So the plan of attack to make this thing less sensitive is pretty simple. Let's try to have that signal a little higher up and prevent any spurious stuff to go in it. So what we are going to try to do is what is exactly in the standard circuit has been omitted here, is that usually you try to have the crystal to shoot in a resistance that's called R load, which is about the same as the resistance of the crystal, so it should be 100 or 200 ohms. And then you put a fairly high capacitor to the ground, and that will have one benefit, which will be it will reduce the noise pickup here from an antenna problem, because now I'm going to go in RF in a load of 100 ohms instead of going into a load of 2 kilo ohms. It also usually is done not for that reason. It's done to prevent the kickback from the stage to influence the crystal too much, so it shorts the feedback to 0. But I'm already low on signal over here, so I don't want to go too low, so I'm not going to go 100 ohms, but I'm going to go 330, something like that. 330, and I'm going to put a cap to ground, something big. And so this is going to bite me in another direction, is that the signal is going to be less, and I want a bit more. So here I had 10K, and I'm going to get that down to 3K. So that should get rid of two problems. This is going to make the signal level here much higher. It's way too low right now. And this is also going to shunt that path to the ground and make the antenna pickup program much less. Hopefully. Okay, so here's my improved circuit. So on the feedback bias resistor, now it first hops from the output to this intermediate point and back to 330 ohm and back to the input, and it's decoupled by this 0.1 microfarad capacitor. And then the 10K resistor has been dropped to 3K. Now in reality, when I tried it first, I didn't do those two changes at the same time. I first tried the decoupling, got better. Then I tried to lower the resistor. I tried first 5K and then 3K. And as long as it kept better, I kept doing it. But no, it took me an afternoon here. I wanted to do a little faster for the video, so I applied two changes at the same time. I saw a notable improvement. Here we go. And yeah, you can see that there's still a tiny bit of jitter, but it's really reduced, and then the sensitivity to nearby antenna is much better. Now if I touch the quartz, it still does something, but it's much better than before. The jitter at the output is now fairly acceptable. Let's try to make it even lower. I had to calculate it, so it's about 100 ohms at 10 megahertz, and that gives me 80 puff, but I put 100 puff and see if that improves things. What that does is basically it shorts this at high frequency, so it will bring the gain closer to unity, and hopefully make it still high gain enough at 1 meg, so it oscillates, but low gain for the 10 megahertz spurious signal. Okay, so I haven't added my big ugly 100 puff capacitor. I didn't have a smaller one to lower the gain and further reduce high frequency pickup. And now if we get it, it's a lot better. It's as clean as it was when I was powering it up with the clock not on. So look at that. I think that did it. So I think that's as far as I want to go. We could go further, but then we risk we have the risk of overdriving the quartz, which is not a good thing for reliability. And of course, this is space stuff, so you don't want to get any close to that. Right. So that's the same circuit, but without the benefit of what we've put here, and it's just full of jitter. When you compare to the improved circuit on the bottom, how do I do that? I do this, and here we go. Much cleaner with the addition of a few components. So why they didn't do that, I don't know. Putting the cover over the clock wouldn't do anything. It would protect the outside, but not what's inside. So I guess they flew like that, and since it was a backup clock and it's divided by 10 million cycles anyhow, they weren't sensitive to it, and they say, hey, it works, it's within spec. Or maybe they just didn't see it. We are blessed with modern scope that catch glitches and that zero you in on the stuff right away. When you have an older scope, you are not going to see it as easily. So you might ask me, will I fix it in the clock? No, I'll know it flew like this originally, so I leave it like that. It was an interesting thing to understand why it was doing it, and to make sure that we didn't have a broken clock. That's how it's supposed to operate. That's how it flew. and the people were just fine with that being, you know, not optimal for signal looks, but okay for the mission. Alright, hope you enjoyed and learned something about crystal oscillators.